If your score jumps around every time you rerun a train test split, you're not measuring performance, you're measuring luck. Let's do k-fold cross-validation and read the mean and variance properly. You have a model and a data set, and your single split keeps giving different answers. I will show you how to get a stable estimate of performance. You will learn to run simple baselines, compare them across folds, and report both mean and spread so your conclusions are honest. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Cross-validation solves a common pain in model evaluation. When you split data once, your score can reflect the random split more than the model. K-fold evaluation repeats training and testing on different slices so you see variation and central tendency. People reach for it when data sets are small to medium and when they need reproducible model comparisons. The trade-off is more computation versus a more reliable estimate, compared with a single train test split that is cheap but unstable. Think of cross-validation as a voting crowd. You shuffle the data into K groups. Each group takes a turn as the test set while the others train the model. Success looks like a low average error and a small spread of errors across folds. If the spread is large, your model or data is fragile. If the average improves over a naive baseline, you have something worth tuning. Here's the simple idea with a tiny concrete example. We will use a small, almost linear dataset of 10 points and test a naive baseline that predicts the training mean. We will try one holdout, then 5 folds, then compare mean versus median, then run leave one out, and finally refit the chosen baseline on all data, while reporting cross-validated error and spread. This workflow shows both central tendency and variability, and it keeps the same dataset for all steps. We will build a baseline evaluation pipeline that prints mean absolute errors and a compact baseline report. Now we'll run a single holdout test to see how misleading one split can be. This snippet runs a single holdout test using a mean predictor. The lists X and Y define a small, almost linear dataset. The variable K chooses the first 7 points for training and the remainder for testing. The value mu is the training set mean of the targets, and we predict that constant for the test set to compute mean absolute error. Increasing K leaves fewer test points, which makes the estimate swing more. Decreasing K creates a larger test set, which tends to stabilize the number. The printed MAE is one split's verdict, which can easily mislead you about true generalization. Next, we will partition the data into 5 folds to see stability across multiple splits. This snippet estimates performance with 5-fold cross-validation. We partition the data into 5 contiguous folds of size 2, using each pair as test once and the rest as training. For every fold, the variable mu is the mean of the training targets, and we compute the mean absolute error on the held-out pair. The list out collects the per-fold errors so you can see stability across splits. More folds reduce training size per fold and can increase variance of per-fold scores, but the average tends to be a more reliable estimate. The printed list shows how errors fluctuate by fold. Now we will compare a different central tendency to see which baseline resists outliers better. This snippet compares mean versus median baselines using the folds. For each fold, we compute the training set median by averaging the 2 middle values and evaluate mean absolute error on the held-out pair. The variable EAD accumulates the median baseline's total error across folds. We then compare the average median error with the average from the mean baseline already stored in out and select the better one. Using the median can resist outliers, while the mean can be slightly better when the relationship is near linear. The printed winner tells which central tendency generalizes better here. Next, we will push to leave one out, so each point gets its own test verdict. This snippet runs leave one out cross-validation to reduce split luck. Each iteration leaves one target out for testing, uses the other 10 minus 1 targets to compute the training mean, and stores the absolute error for that single prediction. The list S collects errors across all 10 possible holdouts. We then compute the average and the standard deviation, summarizing both central tendency and variability of performance. Leave one out uses K equal to the dataset size, which often stabilizes the average at the cost of more computation as data grows. The printed mean and spread provide a precise, split-agnostic summary you can trust. Finally, we will fit the chosen baseline on all data and report the cross-validated summary for future comparisons. This snippet finalizes a simple, trustworthy baseline. We refit the selected baseline on all data by computing the full data mean, which is the single parameter for the mean predictor. The variables M and S come from leave one out cross-validation and summarize expected error and its variability across all possible single-point holdouts. Packaging both the fitted parameter and cross-validated estimate makes the baseline reproducible and easy to compare against future changes. The printed line is a compact baseline report you can trust for quick comparisons. Recap in 3 short points. What it is: K-fold cross-validation repeats training and testing on different splits to estimate both mean performance and its variability. When to use it: use this when a single split gives unstable results or when you need honest model comparisons on small to medium data. One caveat: more folds or leave one out give more precise averages, but cost more computation and can increase per fold variance. Next step, take this pipeline and swap the mean predictor with a real model, then run the same folds and compare both accuracy and timing as you scale up to larger datasets. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.